All right. Hello. So in this section, we're going to be going over an introduction to calculus, where we're going to talk about finding limits. What are limits? How to find limits using tables and using graphs. And then we're also going to talk about one-sided limits as well. So the idea with limits here is that it's going to incorporate this motion when we're actually evaluating a limit, which is something that we haven't really done before up to this point. So let's start off here with the introduction to limits, just so we can see what a limit actually is. So let's consider this function f of x equals x squared minus 4 over x minus 2. So this is a rational function. So we could simplify this function by factoring the numerator as x plus 2 times x minus 2. And then the denominator just does not factor. It stays as x minus 2. And then we can cancel common factors of x minus 2. And we're left with x plus 2. So that means we can actually graph this function pretty easily, because we can just graph the linear function y equals x plus 2, which is of course a y-intercept of 2 and a slope of 1 over 1. So that would look something like this. So that is the graph of y equals x plus 2, and it's almost the graph of the original, but remember that when we cancel common factors, when we're simplifying a rational function, that means there's a hole. So there's a hole when x minus 2 equals 0, which means there's a hole at x equals 2. So at x equals 2, there's going to be a hole, which means the original function would actually look something like this. So our original function, the graph of it looks like this. So we know that f of 2 is undefined because there is a hole when x equals 2. So what we're going to do with limits here is we're actually going to ask ourselves, what are the y values getting closer to as x gets closer to 2 from both sides? So basically we're saying what function value is the curve getting closer to as x gets closer to 2 from both sides. So you can see how there's this motion involved where we're getting closer and closer to a certain value from both sides. So when you're given a graph, it might be a little bit more obvious. You can see that the y values are getting closer to the hole, which is a y value of 4. So we would say that as x gets closer to 2, the y values are getting closer to 4. That doesn't mean that f of 2 equals 4. That just means that the y values are getting closer and closer to 4. So another way we're going to be doing this for a little bit in this section is creating a table. So you can see we essentially just have an xy table right down here. So we have x in the first row, y in the second row. Y is f of x, the original function. And in the middle, we have the value, the x value in question, the x value of 2. And we know that if we plug into the function to get the y value, it is undefined because you would get 0 over 0 because there was a hole when x equals 2. So you can see here that I chose some x values. I already pre-chose some x values that are both getting closer to 2 from each side. So you could have chosen x values that are maybe just a little bit different, but hopefully you agree 1.99, 1.999, 1.9999, and same idea for the right-hand side. They get closer and very, very close to 2 from the left and very close to 2 from the right. So what we're going to do here is we're going to take these one at a time, and we're going to plug them into our function. So if we plug in 1.99 into our function, we would get 3.99. If we plug in 1.999 into our function, that would give us 3.99. And then lastly, if we plug in 1.9999 into our function, we would get 3.9999. So if we do the same thing with these values over here on the right, if we plug these into our function one at a time, I'll just do this kind of quickly here, we would end up getting 4.0001, 4.001, and 4.01. So now what we want to do here is ask ourselves, what are these y values getting closer to from both sides as x gets closer to 2? So it looks like from both sides, as we get closer and closer to this middle value, it looks like both of these values from the left and from the right are getting closer to a value of 4. And that's exactly what we're going to be doing here with limits. So what we would say here is the limit of f of x as x approaches 2 equals 4. So the answer to our limits, the answer is going to be a y value. So in limit notation, we're going to be seeing this notation a lot in all of these sections here. The limit notation, which I have more formally denoted on the next page, is this right here. And you read this exactly the way that I have it written right up here. So the limit of f of x, or the limit of x squared minus 4 over x minus 2, as x approaches 2 equals 4, which means the y values are getting closer and closer to 4 from both sides as x gets closer and closer to 2. So what we're going to be doing here in this section, like I mentioned a few minutes ago, we're going to be evaluating limits using tables and graphs. And then in a different section, we're going to be evaluating limits by hand using limit laws. So here is the limit notation just kind of more formally written down. We have the limit of f of x as x approaches a equals, that's what we're usually finding, in this case just equals some number L. So just like we saw on the first page, the function does not actually have to exist at the x value that we're approaching in order for the limit to exist. So just because f of a does not exist, that does not mean the limit does not exist as well. It might exist, it might not. So let's do a couple more examples where we're evaluating limits using tables. So I'll even say this now as we go through this. Using tables is probably one of the worst ways to evaluate limits, just because you're constantly plugging in numbers. You're essentially making like this really nasty XY table, and you're just constantly plugging in numbers. So it's not usually the best way to do it, but it's the way that we're going to start off doing this, just so you can understand what's actually going on. So for example, if we want to evaluate the limit of 3x squared as x approaches 4, what we're going to do every time we want to evaluate limits using a table is we want to choose x values to the left and to the right of a, of whatever x is approaching, such that the values are getting closer and closer to our value of a. So you can see here in this example that I have written right down here, we have x approaching 4. So 4 is going to go right in the middle on our little x, y table. 4 goes right in the middle. And then I choose values that are less than 4, but that are getting closer and closer to 4 from the left. And then I also choose values that are greater than 4, but that are getting closer and closer to 4 from the right. So if you wanted to, for these values right here, you could have technically, there's no like set values that you have to choose. You could have chosen like 3.8 for this one. You could have chosen then 3.89 or 3.99999. There's no set values for these. You just need to make them getting closer and closer to your value of 4 in this case from both sides, and they should get really close to your value of 4. Like you shouldn't have values such as 1, 2, 3. You usually should have decimals getting very, very close to your number in the middle. So just like the first example on the first page, now we're going to take these values one at a time, and we're going to plug them in to this function. So if we plug in all of these values into 3x squared, we would get these 3 values. So maybe just verify, plug it in your calculator, make sure you get the same exact thing. Now let's go ahead and plug these 3 values separately into 3x squared again. And we would get these 3 values here. And then as always, when we are using this table technique, now you're looking at both sides of the table from the left and from the right of your value, and you're asking yourself, what are these values getting closer to from the left side? And what are these values getting closer to from the right side as we approach this middle value? So hopefully you agree when you're looking at this, it looks like from both sides, we're getting closer to a value of 48, right? So for this specific example, you might be saying to yourself, well, what happens if we just plug in 4 into the function? If you plug in 4, you will actually get 48. So this is something that we're going to see why that is. It has to do with what type of function this is. It has to do with continuity. We'll see when we're allowed to just plug it in and actually get the answer, because that's obviously a lot easier. But just always remember, you're not necessarily trying to find the y value per se for these. So that's why we're starting off by creating this table. So what we would say when we're answering this question, we would say the limit as x approaches 4 of 3x squared equals 48. So once again, I can't stress this enough. Even though we're going to see going forward, when you can plug it directly into the function, there's a specific reason that tells us that we can plug it in when we actually get there. But don't just assume that you're always going to be able to plug in what x is approaching into your function and get the correct answer, because a limit is not always the same as the function value. It is a big difference. All right, so let's see the next one. Let's say we have this function right here. So we may or may not have dealt a lot with trig up until this point in the class, but let's just go ahead and take a look at this example. So the limit of sine of x over x as x approaches 0. So sine of x is a trigonometric function. If you graphed this function over here, just to kind of get a nice visual, the graph would look something like this. So when we want to make a table for this, x approaching 0, so we have this table. We have what x is approaching directly in the middle. We have this xy table, and then I chose values of x that are getting closer to 0 from the left side of 0 and the right side of 0. So I chose negative 0.03, negative 0.02, negative 0.01, and then 0.03, 0.02, and 0.01. So now we're going to take these values one at a time, and we're going to plug them directly into this function. Just keep in mind, like I said, if we have dealt with trigonometry in our course and you are plugging this in your calculator, make sure you're using radian mode in the calculator. If we haven't dealt with trig in our course, then don't worry too much. Hopefully the concept makes sense for this table though. So we're going to plug these in one at a time, and we would get all of these values right here using our calculator. And then as usual, we're going to ask ourselves, what are these values getting closer to from the left and from the right? And it looks like from both sides, the y values or the function values are getting closer and closer to a value of 1. They're getting very close to a value of 1. Also notice that if you plugged in 0 into the function, sine of 0 over 0 is undefined. So this is another example of one that you can't just plug directly into the function. So what we would say for this answer is that the limit as x approaches 0 of sine of x over x equals 1. Okay, on to the next topic. So for the next topic, that was evaluating limits using tables. Now we're going to evaluate limits using graphs. So the great thing about graphs is that usually there's going to be, well, always, there's going to be no calculations involved when you're looking at a graph. You just have to look at it to figure out your answer. So there's going to be a couple different things that we have to worry about when we're evaluating a limit, when we're looking at a graph. And that's going to be that the function value f of a will not always equal the limit value. So usually when we're finding f of a, that's just finding the y value, finding where the filled in circle is or finding where the curve is when x equals a. But finding the limit is just going to be a little bit different. So it's not always going to be the same thing. So for the first example here, just to see the kind of 3 different possibilities for now for how we might see these in the next few examples, you might have this curve. Notice that this is a continuous curve. That's pretty important. but we have this curve. If we wanted to find f of a and the limit as x approaches a of f of x separately, for f of a, all you have to do is find a. You go to the curve, find the filled in curve itself, find the filled in circle or the curve itself, and then see what the y value is. So f of a is whatever L is for this case. Now for the limit, when we're evaluating the limit, we always have to incorporate motion from the left and motion from the right. We're going to find A, find where the curve is, but then you're going to ask yourself, what are the y values approaching? What is the curve getting closer to as you get closer to A from the left and closer to A from the right? So in this specific example, once again, this has to do with continuity, but we'll talk about that in a different section. For this specific example, as we approach it from the left and the right, it's approaching this value here, which is also whatever L represents. So in this specific case, the function value or the y value is actually equal to the limit value, which once again will not always happen. Let's see when it starts to look a little bit different. So we have this curve, we're going to evaluate f of a, and we're going to evaluate the limit as x approaches a. So when we evaluate f of a, here is a, and we're going to find the curve, there is a hole and there's no filled in circle anywhere. So f of a is actually undefined. So f of a is undefined because there is a hole when x equals a, and then there's no separate filled in circle anywhere when x equals a. So now, so you can see the difference here. Now for the limit as x approaches a, we find a, we go up to the curve, and we're going to approach a from the left and from the right. So by now you can see, I think it's a good idea to put these little arrows in from the left and from the right, kind of like you're riding along the curve on a roller coaster from both directions, and they're gonna smash into each other. So your x is gonna approach a from both sides. And now you're asking yourself, what are these values getting closer to? These values are getting closer to this hole. This hole has a y value of L, and that's the answer to the limit. So that's like one of the most fundamental differences between the function value and the limit value. The function value might not be defined. F of a is undefined for this one. That doesn't mean that the limit is undefined. The limit might still exist. The limit can and will be the y value for the hole. All right, so let's see another one. Let's see one that looks pretty similar to what we just did, and we're going to evaluate f of a and the limit as x approaches a once again. So f of a, we find a, and there's a hole here, but there's a filled in circle right here. So f of a does exist. I'm just going to put exist. It's whatever f of a happens to be. It's just labeled f of a over here. So f of a does exist. Let's compare this to the limit. The limit, we find a, and we find the curve directly to the left and to the right of a. So the curve is right here. As we approach it from the left and from the right, it's approaching the hole, which once again, I'll say this a million times, the hole can and will be the answer. The hole's y value can and will be the answer to our limit. So notice here that these both exist, but they're not equal. All right, so these are some examples that we're going to see. Let's actually get into some actual graphs here so we can see some examples. So let's take a look at this graph of this function f of x, and then we want to answer all of these questions. I'll leave it like that. So we have the first one. We have the limit as x approaches -2. So first, when you do these, I think it's a good idea just to make sure you're comfortable like reading graphs pretty quickly. Find what x is approaching on the x-axis, which is -2. And then you're going to go vertical up or down until you find where the curve is. So the curve in a filled-in circle is right up here, right? So as x approaches -2, since we're doing a limit, that means we're trying to figure out what are the y values approaching from the left and from the right as x gets closer to -2. So that's going to be the little arrows that I have drawn in, and it's approaching this hole value and the whole value is the answer to the limit. The whole's y value, I should say, which is a y value of 5. So the limit as x approaches 2 of f of x equals 5. All right, always just remind yourself too that when you are answering these questions, you're asking yourself, what are the y values getting closer to as x approaches your value from the left and from the right? All right, next one. This is a question that we could have done a while ago, hopefully. F of negative 2. That's just finding the y value. F of negative 2, there's a filled in circle right up here. So f of negative 2 is the y value for the filled in circle, which is 3. So f of negative 2 is 3. Notice that these are not the same. For the next one, we have the limit as x approaches 4. So x is approaching 4. We're going to go vertical, find the curve. So we can see it's pretty similar to the one that we just saw a second ago with a hole in the curve and then a filled in circle. So the limit as we approach from the left from the right is going to be approaching this hole, which has a y value of 7. And then for f of 4 is going to be the filled in circle, which is a y value of 2. So even though some of you are probably saying to yourself right now, like, do you have to draw the arrows in when you're finding the limit? You don't have to, but you should always, don't just say, oh, it's the whole value really quickly. It's a whole value, which is y equals 7. You can do that and get the correct answer, but you should always at least consider in your head the arrows, because that's what a limit is. It's the limit that you're thinking about it approaching your x value from the left side and the right side. We'll see why that's important in a few pages. All right, and then the last one here, we have the limit as x approaches, once I get this off my screen, as x approaches 6. So we find 6, we go up to the curve. There's nothing weird happening, right? There's no holes or discontinuity. The curve looks like it's continuous here. So we're going to do this one the same way we always do it though with limits. We're going to approach 6 from the left and approach 6 from the right. That's approaching this y value. Let me change my arrows a little bit. That's approaching this y value right here, which is a y value of 7. So there doesn't have to be a hole when you're evaluating a limit. If it's just a nice continuous chunk of the curve, then the limit will actually equal the function value. Okay, let's see a few more here before we get to one-sided limits. So let's say we have this graph. So before you look at the graph, let's say we have this piecewise function. This is a piecewise function, right? Remember piecewise functions? It is one function composed of 2 or more functions over different domains. So f of x equals 2x minus 4 when x is not 3, but then it equals negative 5 when x is 3. So if you graph this, it would look something like this right here. So here is the curve when x is not equal to 3, but when x does equal 3, it is down here at negative 5. All right, so for the first one, we have the limit as x approaches 3. So as x approaches 3, we'll do this one a little bit quicker. As x approaches 3 from the left side and the right side, it's approaching this whole value, which is a y value of 2. And then for the next one, we have f of 3. So f of 3 is going to be the filled in circle, which is down here, which is a y value of negative 5. And then lastly, limit as x approaches 1. So as x approaches 1, it looks like there's nothing crazy going on. There's no holes or anything. It's just a continuous part of the curve. So as x approaches 1, as we approach it from the left side and the right side, it's approaching this y value, which is a y value of negative 2. So just like the one we saw on the previous page, anytime you have the limit over a continuous part of the function, it's just going to straight up equal the y coordinate. Right. So now we're going to jump into one-sided limits. So all the questions we've just seen in the past few minutes here have looked something like this, right? You have this curve, and then maybe there was a hole in it, and then we would say, what's the limit as x approaches 2? So that's what we've seen so far. Now what we're going to do is we're going to spice it up a little bit, and we're going to see stuff like this. So now we're going to have this big, you probably see right away, you probably see there's this big jump in the curve. So now we're going to be finding the limit for like this one, for example, as x approaches -2. And we're going to be considering what's happening from the left side, what's happening from the right side, and this will bring us into one-sided limits. So this is something that we've talked about already. We just really haven't called them one-sided limits. We haven't seen the notation, but now we're going to be approaching an x value, a limit as x approaches some value, from the left side and from the right side separately. So the notation for this, for a left-handed limit, is going to be this right here. So the limit as x approaches a, notice that you have this little negative superscript. This little negative superscript means from the left. So you would read that as the limit as x approaches a from the left. And then similarly for from the right, that's going to be, excuse me, that's going to be this notation right here, where you have this little positive superscript, which means the limit as x approaches a from the right. So two different handed limits here. We have a left-handed limit, which is this notation, and a right-handed limit, which is this notation right here. As always, too, make sure you can understand mathematical notation, but you should also be able to read it off in words correctly as well. All right, so let's see an example. So we have this piecewise function, but let's say we already have it graphed for us to make it a little bit easier. So let's say we have this right here. We have these two graphs, or sorry, we have this one main function composed of two little sub-functions, so it's graphed out. And the first one we want to answer the limit as x approaches 1 from the left side. So usually for this, I like to do the same thing that we start with from the other ones. Find 1 on the x-axis, and then go vertical and see what the function's doing. So that's, of course, where this big jump is in the graph. So if we're approaching it from the left side, you need to ask yourself, which curve is to the left of x equals 1? And that's going to be this part right here, right? So as we approach 1 from the left, that's going to be approaching 1 from the left side of the curve, which is going to be this arrow that I'm drawing in poorly right now, and that's approaching that hole, which is a y value of 2. So as we approach 1 from the left hand side, that's approaching a y value of 2. Now we're going to do the same thing on the other side. We're going to approach 1 from the right. So this is the curve that's on the right side of x equals 1. So when we approach 1 from the right, and this is where it kind of seems a little bit confusing maybe, because when you're approaching from the right, notice the arrow is actually pointing to the left, right? From the right means you're coming back from the right side, which is actually pointing to the left. So as we approach this value, it's approaching a y value, that filled in circle, which is a y value of 4. So as usual, limit answers can be the y value to a hole. It might be the y value to a filled in circle. It might be the y value to the curve itself. It just completely depends on what's going on with the curve at that specific x value. All right, let's see another little concept here. Basically bringing everything from today together with equal and unequal one-sided limits. So you can see in the example that we just did, these are not the same thing, right? These values, the limit from the left does not equal the limit from the right. This is going to help us evaluate the limit in general. So we're going to use these one-sided limits to help us figure out if the general limit exists or does not exist. So this is what I call, as I just said, what we were doing in the beginning of today, I call this a general limit where it's not a one-sided limit. So the limit as x approaches a. If it's not a one-sided limit, I just refer to that as a general limit. So the idea here is if you do the limit from the left and the limit from the right, and they are equal to each other, they both equal the same thing, then the limit in general exists, and it also equals that same thing. So that's what we've done a lot of in the first several examples that we were doing. If the limit from the left equals the limit from the right, then the limit in general is also that same value. So now if you have something where the limit from the left does not equal the limit from the right, then the limit does not exist. So does not exist, this is kind of a very common thing that we're going to see in these examples. We abbreviate this with DNE. Does not exist, DNE. So for example, in the question that we just did a second ago, if we were doing the limit as x approaches 1 in general, the answer for this is does not exist. The limit does not exist because the limit from the left did not equal the limit from the right. All right, let's see a couple examples of this one. So let's use this graph to determine the answers to each one of these. So we have, for the first one, the limit as x approaches -2 from the left. So when we go to -2, we can see there's this big jump in the curve, right? So as we approach -2 from the left side, that's going to be this part of the curve over here, right on the left side to the left of -2. So as we approach -2, it's approaching this hole, which is on the x-axis, which is a y value of 0. So the limit as x approaches -2 from the left equals 0. As we approach -2 from the right, the limit as x approaches -2 from the right, that's going to be this part of the curve right here, because that's on the right of -2. So as we approach -2 from the right side, notice I'm not like going over -2, I'm going right up to where x equals -2 is. As we approach it from the right, it's approaching this hole, which is a y value of -2. And then now the limit in general, so the limit as x approaches -2, you can go back to the graph if you want and say, well, the limit from the left side does not equal the limit from the right side. But usually for these, most of the time I should say for these, is you're going to end up having already done the one-sided limits. So you can just compare them really quickly. So if the limit from the left does not equal the limit from the right, the limit in general does not exist. So you can also see this really quickly because there is a big jump in the curve. If there's a jump in the curve at that x value, that means the one-sided limits will not be the same, and that means the limit in general will not exist. For the last one, we have f of -2. So f of -2 is just where the filled in circle is, or the curve itself, which is a y value of -1. So just take a minute to look at this. When you have 4 questions all dealing with -2, the same x value, and we actually got 4 separate answers. Sometimes you're going to get 4 different answers. Sometimes you'll get all the same answer. Sometimes some answers will be the same and some answers will be different. So before limits, you could really only do one thing with -2, and that would be f of -2. Now we have all of these other questions that we can answer. All right, let's see one more question here. Let's use this graph to answer all of these questions. So the first one, we want to do the limit as x approaches -3 from the left. So find -3. -3 is right here. Find what's going on with the curve when x is -3. So there's this hole. There's no filled in circle. There's just this hole. So as we approach -3 from the left side, it's approaching this hole, which is a y value of 2. Let's do the next one. Let's approach -3 from the right side. So as we approach -3 from the right side, it's also approaching this hole, which is still a y value of 2. And now for the limit in general, just the limit as x approaches -3, since the limit from the left equals the limit from the right, this limit exists, and the answer is also 2. So this is an example of one. We could have done this question from before we talked about one-sided limits, right? Because if we look, it's approaching it the same thing from both sides, so we knew that the answer was 2 without even talking about the one-sided limits. All right, and then for next one, f of -3. So f of -3, the curve doesn't exist at -3 because there's a hole here, and then there's no filled in circle anywhere, right? So f of -3 is undefined. So something you could do, notice that when I'm talking about limits, I say does not exist if a limit does not exist. If a function value doesn't exist, I say undefined. You could say does not exist for this as well, if you really want to. I prefer to say undefined rather than does not exist. For limits, you have to write does not exist though. All right, next one we have two more. We have limit as x approaches 0. So when we take a look here at x equals 0, there's a big jump in the curve. So this is just a general limit. So for this one, we need to consider the limit from the left side, which is going to 0, the limit from the right, which is going to 3. So since there is a big jump in the curve, that means the limit from the left does not equal the limit from the right. So that means the limit in general does not exist. Okay, and then the last one, we have the limit as x approaches 4. So x approaching 4. So here is 4 right here. Notice that when you find the curve, when x equals 4, it's a continuous part of the curve. There's no holes or anything. So as you approach it from the left side and from the right side, you're going to notice that it's approaching the y value of the curve itself, which is a y value of 4. Okay, so that's it for this section. So make sure you know how to do the notation for limits. You know how to read off the notation in actual words. You know the one-sided limit notation and how to read it off. You know what a limit is. And you should know how to do the tables for limits, even though I'm not going to be focusing on those going forward. You should still know how to do the tables as well.